Hello there. Let's talk about area again, except this time we're going to talk about trapezoids. So you should have some notes about the trapezoid approximation method somewhere. And I'm going to move this so my earring doesn't bang on my microphone. Hopefully that helps. So if we do the trapezoid approximation method, it's kind of like a leveled up version of doing the rectangle approximation method. And why is my video dark? Oh, who knows? Let's do it. So here's the thing. Rectangles are great. Love rectangles. Super easy, base times height divided by 2. But trapezoids are usually better. All right? So if we want to do a trapezoid approximation method for that same region we did in the other set of notes, if I wanted to split this up into 4 regions, and instead of using rectangles, don't draw this, instead of drawing rectangles that like obviously go over or under, okay? We could say, you know what, there's a better way. Draw up your partitions and then connect one endpoint to the other endpoint, like so, and then you get this shape. And if I take that shape and I rotate it 90 degrees, it looks like that, which is in fact a trapezoid. It has a parallel base and another parallel base and 2 non-parallel sides. So there's a trapezoid. That's why these are called trapezoid approximation method. If I connect this to that, I get another trapezoid. If I connect this to that, like, wow, that's perfect, I get another trapezoid. If I connect this to that, I get another trapezoid, and I am feeling pretty darn good about that area. Not a lot of overs, not a lot of unders, just like a pretty good fit here. So if I can find the areas of those trapezoids, then I have the trapezoid approximation method, all right? So the area of a trapezoid, this is something that you need to memorize. I will do some math magic in front of you when I see you next in real life. But the area of a trapezoid, the formula for it is h over 2 b1 plus b2. The height of the trapezoid divided by 2 times the sum of the bases. Now, in this picture over here, if I look at this trapezoid, the height of the trapezoid is technically right there, because remember, when I turned that trapezoid on its end, it looked like this. And the bases of the trapezoid are actually its heights in the picture. So there's a little bit of like head rotation you gotta do, like a dog with a high-pitched sound, but then you can get the values you need for the area of the trapezoid. Okie doke. Let's do it. So it says draw 4 trapezoids that can be used to estimate the area between the graph of that quadratic that we did last time and the x-axis on the interval from 1 to 3. Then estimate the area. Is this estimate over, under, or the real value, and why? All right, so let's draw it first. If I want to go on the interval from 1 to 3, and I want to split it into 4 subsections, and I want to create trapezoids, I just connect the dots. And holy moly, does that look like a pretty dang good estimate? All right. So if I wanted to find the area of those trapezoids, now I'm going to do it off to the right here. You have more space on the left, but I don't want to, swing left and right here. If I want to find this area for trapezoid number 1 right here, my height is technically here. B1 is there and B2 is there. It doesn't matter which is B1 and B2. All right. So if I want the area of trapezoid number 1, I'm going to do h over 2, because my height is a half, because remember, these are half width intervals. H over 2, B1 plus B2. Well, B1 is f of 1, and B2 is f of 1.5. And then trapezoid number 2 has the same height of 0.5 over 2, except for trapezoid number 2, B1 is the B2 from last time, and B2 is over there. But really, if you pause and look at it, you're like, oh, no, I get this. So base 1 is f of 1.5, base 2 is f of 2. Yeah, I used a height twice. Who cares? That's what I'm doing. And then for my third trapezoid, for my third trick, for this trapezoid right here, B1 is f of 2 again, and B2 is f of 2.5. So then I have 0.5 over 2, f of 2, f of 2.5, and the fourth trapezoid, f of 2.5, and f of 3, because that last trapezoid would be this guy with heights at f of 2.5 and f of 3. Okay. So then I got to find that whole thing by adding everything up, but oh my God, even in Desmos, this is going to be kind of annoying, so let's try to shorten it up. All of these trapezoids for this example have the same h over 2. So I am going to factor out that 0.5 over 2 and say, all right, what am I adding? I'm adding f of 1 plus 1.5, plus 1.5 again, plus 2, plus 2 again, 2.5, 2.5 again, f of 3. Every interior height, which becomes a base of the trapezoid, is doubled. The endings are singles. So if I want to find the area of all these trapezoids, I'm going to have f of 1 plus 2 f of 1.5s plus 2 f of 2s plus 2 f of 2.5s plus an f of 3. And now I'm going to use handy dandy Desmos. Blink. All right, and in Desmos, which I pulled up already, this was f of x equals what now? X squared minus 2x plus 2, x squared minus 2x plus 2. And we are going to do, I type the fraction button because it helps, fraction 0.5 over 2, f of 1 once, plus 2 f of 1.5, plus 2 f of 2, plus 2 f of 2.5, plus f of 3, 4.75. Ta-da! And so the estimate for this trapezoid is going to be area equals 4.75. Is this an overestimate or an underestimate? Well, I said at the time, holy moly, that's a good value. But if I like zoom in as much as I possibly can, you can kind of tell that the graph is like this, and my lines are above it. Kind of like, what's that thing in chemistry? The meniscus, which is a tendon, but also it's the, when you look at water in a beaker, right, doesn't it have a little surface tension dip in it? Just like that, this kind of has a meniscus, okay? So why is the trapezoid an overestimate? Because the meniscus looks like that, which means because the graph of the function is concave up, the trapezoid line is above the function itself. So it says, is this an over-under of the real value and why? This is going to be an overestimate because the function is concave up. Okay? So trapezoids, you add up a whole bunch of stuff, h over 2, b1 plus b2. If your height is the same, if your subintervals are all the same width, you can factor out the height and then do b1 plus b2. Duplicate b2 because it's b1 next, and so on, okay? And whether you have an overestimate or an underestimate depends on the concavity of the function. Now, the next part says, flip back a few pages. What do you notice about the trapezoid and LRAM, MRAM estimate? And I just realized that there's a typo right here. So everybody fix Mrs. Vibber's typo and change that to RRAM. Unless I've changed it on your copy already, then you don't have to. That should say, what do you notice about the trapezoid estimate and the LRAM, RRAM estimate? If we go back to this same picture, the RRAM estimate is 5.75. The LRAM estimate is 3.75. And the trapezoid estimate is 4.75. Guess what? That is not a coincidence. Not a coincidence. What do you notice? Trapezoid is exactly halfway between L and RRAM. That's because trapezoids are always the average of LRAM and RRAM. Always the average. And you know why? Because guess what? We use the left side height, and we use the right side height, and we divided everybody by 2. So trapezoids are always the average of LRAM and RRAM, which makes them, by definition, usually better than LRAM or RRAM. Okay? So trapezoid's always an average of LRAM and RRAM, and a function's concavity determines whether trapezoids will yield an over or an under estimate. So just to recap, if concavity tells you about whether trapezoids are over under, whether a function is increasing or decreasing, was how we knew if rectangles were an over or an under estimate. Okay? So trapezoids over under depends on concavity. If they are rectangles and somebody asks over under, then we want to look at whether that function is increasing or decreasing. All right, flip over to the back. We just got a little bit more to do. This one says, fill in the blanks. Estimating the area beneath y equals e to the x on the interval from a to b using RRAM would be a blank estimate because e to the x is a blank function. Well, let's see. Y equals e to the x is an exponential function that's increasing, and it looks like that. And if I think about RRAM, if I picked any subinterval, a to b, doesn't matter where, and I do RRAM, those rectangles are going to be outside the graph. They're going to be too big. So RRAM would be an overestimate because e to the x is an increasing function. But if again I looked at e to the x and I did trapezoids instead of RRAM, if I split it up from a to b, and then I drew in some trapezoids, that's where I split it up and connect the dots, those lines would be above e to the x, so again I would have an overestimate. However, it's not because this is an increasing function, it's because it is a concave up function. The increase has nothing to do with the fact that the trapezoids are overestimating. Okay? Okay. And if you're thinking, wait, but how can that be? Look, here's another concave up function. Here's y equals e to the negative x. And if I drew trapezoids in here, they are still overestimating the area of the curve. All right? So concavity determines over-under for trapezoids. All right, last thing. Let's talk tables. So just like in the other one, we usually use RRAM, LRAM, MRAM, and now trapezoids when we have data in tables. Because guess what? When we have actual functions, we can find exact area. We'll get to that. But if I don't have actual functions, all I got is data values, I'm going to have to use an estimate. And to use that estimate, I'm going to need trapezoids or rectangles. That's just the way it goes. So this says, estimate the area between f of x and the x-axis on the interval from 0 to 20 using LRAM in the 6 intervals given. Okay. So if I wanted to, and if you want to, you can always sketch a graph and say, all right, let's see, x goes from 0 to 20, and y goes up to 20 as well. And so if I plot some points here, 0, 4, 1, 5, 5, 9, 9, 12, 11, 15, 15, 19, and 20, 20. Okay, well, there's my graph. Estimate the area between f of x and the x-axis on the interval from 0 to 20 using LRAM in the 6 intervals. Okay, so if I'm doing LRAM, I'm going from left to right. And my intervals are going to have widths of 1, 4, 4, 2, 4, and 5. And if I use LRAM, I'm using the left-hand side of each interval. So I'm going to do 1 times the height of 4, plus 4 times the height of 5, plus 4 again times 9, 2, 12, 4, 15, 5, 19. And then I have to add it up. Let's see, that's going to be 4 plus 20 plus 36 plus 24 plus 60 plus 50 plus 45, that's 95. So let's see, 36, 40, 60, 84, 144, 144 plus 95. Well, that'd be 244 minus 5 would be 239. So 239. If I'm wrong, please somebody tell me when you see me in class tomorrow. All right. And then for B, it says estimate the area between f of x and the x-axis on the interval from 0 to 20 using trapezoids and the 6 intervals given. All right, now I'm using trapezoids. Trapezoid area is always h over 2 b1 plus b2. A word of caution, you can only factor out h over 2 if you have consistent subintervals. We do not. Our subintervals are 1, 4, 4, 2, 4, and 5. Those are not consistent, so I need to do every trapezoid independently, okay? So for my first trapezoid, my height is 1 and my bases are 4 and 5. So 1 over 2 times 4 plus 5. My next height is 4, and then I'm adding 5 plus 9. My next height is 4, 9 plus 12. 2, 12 plus 15. 4, 15 plus 19. 5, 19 plus 20. And it's all supposed to be h over 2, so I'm going to come back and divide all of those heights by 2. Okay? I could have done that while I was writing it out in the first place. I forgot, so I put it in after. As long as you divide by 2, we're fine. Okay, so let's see. What am I going to do here? Well, let's see. 4 plus 5 divided by 2, that's 9 halves. 5 plus 9 is 14. 14 times 2 is 28. 21 times 2 is 42. 2 divided by 2 is 1. That's 27. 2 times 34 is 68. And then I have 19 plus 20 is 39. 39 times 5 is 195. Public math, I think that's 195 over 2. 39 times 5 is 150 plus 45. Yeah, 195. All right. 68 and 42 is 110. 137. 145. 165. 195 tooths plus 9 tooths is 204 tooths, which is really 102, and 165 plus 102 is 267. And Saved by the Bell, literally, I'm done. If you noticed anything wrong, please tell Mrs. Vibber or send me an email so I can update it in the video. I appreciate it. Thank you for following Public Maths with Mrs. Vibber. Everybody have a great day. We will talk again soon. How do I end this? It's right here. Bye.